statistical scholars, and welcome to the introduction of Chapter 9. There's something I'm going to show you today to relate Chapter 9 to some of the things you've done previously and give you a good picture of some intuition on what we're going to be up to in Chapter 9. So basically what I'm going to do with you first is I'm going to show you, I'm going to show you a few simulations on how to build a sampling distribution or for proportions, for a proportion, sorry. So I have several of these set up to run for you, and I want to show you what this is going to look like. I will also link to this website in the description for this video. That way you have the ability to access this should you want to try this on your own. So the basics of the idea of what this simulation is going to do is it knows what the sample proportion is going to be. It knows that it's about 275, okay? And then the idea is that I am looking at this population and I am going out and I'm grabbing a sample of a specific size. So notice the sample size up here is set to be 5. So the idea is that I don't know necessarily what the true population looks like. That's one of the things you should have learned in Stat 1 is knowing what the population looks like is pretty darn hard. So what we're going to do instead is we're going to go out and we're going to gather samples, look at those samples, and see if we can use those to make predictions on what this population proportion is actually going to be. So in this example, what I'm going out and I'm doing is I'm going to grab samples of size 5, but I'm not just going to grab one because not every sample will be the same. I'm going to grab a couple. So I've got this lovely website that will allow me to generate several samples at once using a computer simulation. And I'm setting it to do sample size 5, and I'm going to make it do, let's say 1,000 samples. So as you look at the stacks that we've got here, and then there's one over here. This tells me that I gathered my 10,000 samples. I looked at the proportion that each of those samples had. So I went out and grabbed 5 individuals, looked how many were my successes, and then calculated that proportion. So like for instance, the last sample that was done, 1 was a success out of 5, so that proportion was 0.20. So as you look at these stacks of dots, if you do a smaller sample, it comes out as dots. They represent all the samples and where they're ending up. So this is like a count distribution, not a frequency distribution. So it's telling me how many I got instead of frequency. So as you look at this, you'll notice that, it appears to have a skew shape. Specifically, it's a skew right. And on here, it also tells you what the mean is, 0.28, which ain't bad, but, it's kind of interesting. I'm going to go through a couple of these before I start comparing them. So let's go to my next set, which is going to be, let's look at sample size 50. So instead of gathering 5 individuals in my sample this time, I'm going to gather 50, and I'm going to generate 1,000 samples. Bonk. Ooh. So as you look at this, my 1,000 samples are all stacked up here. It looks pretty good. It's a little bit skewed or a little bit off of being symmetric, but it's pretty much symmetric. I've got some problems in here. And you look at the mean and it's 0.275. Not too bad, shabby. This guy almost looks like an outlier, but I would have to do an outlier test to determine that. P.S. That's one of the things we're going to do in this class is actually come up with a good way to calculate outliers. In case you didn't like the one that was in Stat 1. Let's look at the sampling distribution with a different size. So now I'm going to do size 200. So I'm hoping you notice I've been changing my sample size and gathering from the same population using random generation. And then we're going to observe what we notice about this. So generate my 1,000 samples. Bam! Sorry, that was a little more dramatic than I intended. Okay, looking pretty, yeah, it looks pretty good, I believe in your notes I did 10,000 instead of 1,000, which made me get a much smoother curve. So I'm hoping you look at this and you're like, it looks pretty, symmetric. This one's a little bit more symmetric than the previous one. And my mean is about 0.275 here. So a couple things. Let me go back to the first one. Let's talk shape. Definitely askew. Relatively symmetric, almost a perfect bell curve. Relatively symmetric. I mean, it's lumpy, but it's, it has a normal shape to it. Here's some other things we want to look at. When it comes to describing distributions, remember distributions do 2 things for you. They tell you how often a value occurs and what those values are. We usually describe shape, center, and spread. I've gone through shape. Let's do center. Mean is about 0.28 for this first one. about 0.275 for the second one, and about 0.275 for the last one. I also want you to pay attention to the fact that 0.275 was actually the true proportion of the population. So the first one, it got close to having its center actually match the truth. So its mean of the distribution was almost the true proportion. Once I hit 50, it turned out that I exactly had it. By the way, 50 is a magic number in this. Once you get above 50, it's going to be very close. And in fact, always about 99% of the time will give you the true proportion as the center. For more on why, go watch your notes. Haha. Because it meets some of the conditions once you hit 50. Okay, that was vague, not vague, but specific. I don't know what I'm doing. Center, woohoo! Okay, now, one of the things that stinks about this random generator is I can't force this all to have the same range. So I'm just going to do range for my spread, because it's pretty easy to do. So this one goes from 0 to 1. Okay, next one goes from about 0.1 to a little bit above 0.5. So I'm hoping you notice this is smaller than half of the previous one, so my spread is getting smaller. And then this one goes from a little bit smaller than 0.2. This is probably 0.1 again-ish, but they didn't include 0.1 on the scale, so I'm betting it's a little bit below that. All the way up to, you know, just not quite 0.4. So clearly it's just getting smaller and smaller in spread. And this is actually what the sampling distribution does. Its mean will match the true proportion, and its spread will be affected by sample size. It will get smaller based on increase in spread. So I'm going to switch over to my notepad now. Sampling distribution. Here's what you need to know. Under certain conditions, this is going to look like what you expect. What do I mean by that? Well, it's going to look normal. And its mean is going to be the true proportion of the population. So be careful, I'm using a lowercase p on purpose because that stands for true population proportion for the entire population. I already said population in that. Okay, what up next? Standard deviation, aka spread of the distribution, or average distance from the mean. That's going to be the square root of the probability of success times the probability of failure divided by sample size. Now, some of this should look very familiar, especially if you've had Stat 1 recently, okay? I'm hoping you remember something similar to it called the normal approximation of the binomial. I'm going to abbreviate because I'm annoying. Okay, so two things. Binomials have something very specific about themselves, like n trials. I repeat, you know, the same process over and over again. N times count the number of successes, and that's called my probability P is probability of success. I'm abbreviating terribly. For more on this, you're going to have to go do some review. Anyway, so the idea is that the normal approximation of the binomial is normal. That's not too surprising, given the name. Okay, this is kind of lame. Its mean is the number of successes. So if this is my probability of success and this is the number of times I'm trying, that's NP. And then its standard deviation is the square root of NP. Come on, P. Q. Now these look incredibly similar now that you have them in front of each other, right? I hope we notice that. Okay, here's the big difference. When you're looking at the sampling distribution, this is about a sample. It's a group of individuals. You have to select more than one person. When you're doing the normal approximation of the binomial, you're counting the number of successes and you're trying to look at number of individual successes. This is about an individual. Just one person, spelled terribly. Okay. So then my natural thought on this was like, oh, well, how are these related? Well, if I take a bunch of individuals and I group them together, I get a sample. Ta-da! You know, so if you average across many individuals, that's how you get from one of these to the other. having a hard time spelling individuals today. Doesn't really matter. Okay, so think about it. Add them all up, divide by sample size. Think about it this way. How do you get from here to here? I take all of them and I divide by sample size. You literally are just dividing by n. Not shocking, right? I mean, I hope not. Same thing here. You literally are just dividing by n. But there's a little bit more math involved. I'm sorry. I know it's very clear that when you have n times p, divide by n, what do you got? P. How do you see the other one? That's a little harder. Let me do that real quick. So if I take the square root of n p q and I divide it by n. This, by the way, what I'm about to do, you do not need to know how to do. This is totally pointless. It's just kind of a fun fact. You could just look at this and be like, oh, I trust her to tell me the truth. Here's why. Let me just show you. Don't ever assume that you will ever have to come up with anything like this on your own. This is not related to your ability to do statistics. It's just how these two are related to each other. How do I do it? I divide by n. So again, average across the sample. So watch this. And this is where the magic comes in. Okay, ready? This is one of those things where now that you've seen it, you know it's a strategy. Coming up with it on your own is like complete balls to the wall, not easy to come up with. So n, oh no, this is under a root, and that's not. So I really want to put it under a root, but I can't do that because then they're not equal. So I'm just going to square it because the square root of a square takes you back to the original. And if you're one of those people who is like, oh, well, the square root of a square technically is the absolute value, aka it's positive, and n is sample size. You can't have negative number of people, so it's never negative anyway. We're good. Now that they're both under a root, you can combine their roots. This is also only true of positive numbers, and these are, oops, I just accidentally wrote that backwards. Sorry about that. There we go. Yeah, I don't know why that happened. And then we're good. Because p is a probability, which can't be negative. Q is a probability, which also can't be negative. N is a count of number of people, which also can't be negative. So there you go. Lo and behold, divide, divide. These divide out to make a 1, and I just get, oh, no, I don't, I just screwed up. That was a square. I lose 1 power, duh. Okay. I wish I could back this up. Oh well, we're all human. And I get p q over n. How do you like them apples? It's pretty good, right? Alright, so that's how they're related. Really, I'm doing a bunch of binomials together or a bunch of normals together is another way you can think of this. So that's the idea behind the sampling distribution, an introduction to chapter 9. For how we're going to use the sampling distribution, this guy, to do stuff and how it's constructed. Please watch the video. Peace out, Girl Scout.